So today is lecture 5 of Harvey's lecture series on tangible incompleteness. Please.
Yes, thank you, Andreas. So you notice that the title is changed: Invariant Maximality, Choice, and Games. This is to reflect some recent insights that haven't been fully checked, and namely the expansion of the topic to invariant games. And this has a lot of ramifications. If this is still steady, lecture 6, I won't start the reversal on lecture 6. Lecture 6 will be, assuming this goes well, will be in fact on invariant choice and games, the proofs of invariant choice in games. And then reversals are started on lecture 7. That's if everything goes fine. And the reversals don't change. So the way this is structured, the invariant choice and game theorems I'm looking at imply the invariant maximality theorems. And the invariant maximality is what is reversed. So there doesn't need to be any additional reversal. The exciting thing that may happen or should happen or hopefully happens with the game approach is that the finite forms are going to be particularly compelling. I also have a new approach to finite forms and invariant maximality as well. So there's been a lot of action on explicitly pi01 sentences. As I've remarked, all the statements so far being considered here in these lectures are implicitly pi01. That is, they're provably equivalent to pi01 sentences over WKL naught. But that doesn't mean that one gets such a nice explicitly pi01 statements, and that's been a challenge for a long time, which seems to be cracking now in a very in a perfect way. All right, so let's talk about what we're supposed to talk about. So last time I did a warm-up. I looked at every invariant widget has an invariant prime maximal gadget, what you could do in ZFC. And we started off with something that I could do in ACA naught. No, excuse me. Yeah, ACA naught, or one of them I think was ACA prime, if I remember right. Well, ACA prime, yeah. ACA prime, and yeah, ACA naught, ACA prime, and Z3. There was another one that was naturally in Z3, and then I ended with one that is in Z, Zermelo set theory, if you remember. All right, the one that is in Z is the one that's really close to the full one. You'll see a remarkable tiny looking change that gives me the full one of the full things that I know that I've reversed to large cardinals. All right, so with that introduction, let's see what we've got here. So we're going to prove the full maximality theorem on all of Q0n to the k. We're going to use our strongest notion of invariance, stronger than the notions of invariance that were used in the previous lecture. And this notion is called lower Z plus order invariance. And the notation in the previous lecture was set up for the introductory material. And that introductory material will also appear in the book as well. But now we present the full derivation, and we begin by making a bridge from the notation of lecture 4. We're going to make a bridge from the notation of lecture 4. So the last theorem proved in lecture 4 reads as follows. This is copying. If I have a set of 2K tuples, and the idea of that set of 2K tuples is it's really a set of order types. It's just a way of, I only care about the order types. So I have a set of order types. There exists S contained in Q0 and K with E maximality. If you remember what that means it's maximal with respect to the property that any two elements of S are any element of S squared is order equivalent to an element of E. I look at the S's such that S squared, every element of S squared is order equivalent to an element of E, and I take a maximal S with that property. That's what I mean by E maximality. This is a review of last lecture. Where for all order equivalent, this maximal thing, S, has an invariance property. The invariance property is for all order equivalent X and Y in Q0 to 1/2, union 1 through N to the K with the same coordinates less than 1, right? The parameters are the same in the same positions, right? X is an S if and only if Y is an S. So that invariance condition is not the strongest, but it's the one that we used last time. And this invariance condition is that what I really wrote? Just a second. There's something here, something strange here. Yeah, order equivalent. Yeah, sorry. Yeah, this is one. Yeah, this is one of the. There are 4 in the book. There are 4 invariance conditions that are featured. 4 invariance conditions that are featured for invariant maximality. This is number 2. Okay, of the 4. Okay, and it's the second weakest. That's not quite true. There's some competitors. Okay, it's not the weakest one. The weakest one has a shift going on. This doesn't have a shift going on. This is the one that's easiest to explain. This is the one that's easiest to explain. All right, so that we proved in Z. And now we're going to change, we're actually going to change the number 1/2 to 1. You see what I did? I changed the number 1/2 to 1, right? And then it jumps from Z to large cardinals when I do that. You see, because the reason is that the parameters are all pushing up against 1, and 1 is the first indiscernible. That's the logic behind that. So when it goes from 1/2 to 1, it jumps from Z way over ZFC. It jumps from Z to these large cardinals, SRP cardinals, stationary Ramsey property, or subtle cardinals. They're all interleaved. Okay. Now the goal of today is we're going to actually prove a sharp form of 6 prime, something with an even stronger invariance condition, an even stronger invariance condition. All right, so let's reconcile to notation. All right, so what I'm going to do, instead of talking about these order types, you can talk about Well, no. To make this particularly neat, I just talk about every subset of Q0 to the 2K. It doesn't have to, I could say finite, it wouldn't make any difference because I'm still treating these as order types. I'm trying to remember whether I want to call this, whether I want to make this finite. I can't remember in the book, but let me put finite. It doesn't make any difference. Every finite subset of Q0n to the 2K has a less than 1 Z plus invariant maximal order root. Order root. This is actually the 6' I was talking about, almost trivially the same. Because this is just being used for order types again, and it doesn't make it isn't important. The n is not important because because n is universally quantified. I have plenty of room. Okay. All right. An ORD root just means, I called it E-maximality right before. An ORD root is just a set in K dimensions such that any pair from it is order equivalent to an element from here. So this is just I'm changing the notation, that's all, in a trivial way. This is another change of notation that is clear. In other words, I take the order invariant subset and I just take the root. The root of a set in 2K dimensions is a set in K dimensions whose Cartesian square is contained in the first set. So these are trivially equivalent to the previous thing. This is just change of notation. Because an order invariant set is nothing more than a set of order types, which is nothing more than a set of vectors. That's all. Yeah, that's just it's simple. And I give this kind of name to the invariance condition. All right. Now we're going to prove everybody in WKL naught plus con SRP today. These are reversed in this book and in this lecture series. These will be reversed. We actually take some theorem, some version of this with an even simpler, an even more basic invariance condition and weaker one, and actually reverse that. Yeah. Okay. The weaker the thing, the weaker the statement being reversed, the stronger is the reversal. This is a bit, I think I did some lying here. This is actually this thing here, minus less than 1 SH. This is this is weaker than this. In other words, this statement is a little bit stronger than the less than 1 SH. Yeah, that was an oversight, but it doesn't make any difference. None of this makes any difference. Okay. These are almost the first 2 of the 6 lead statements in the invariant maximality, all of which are shown to be provably equivalent to con SRP over WKL naught. All right. Now let's talk about the strongest one, because in the book and today we're going to prove the strongest invariant maximality theorem of the in the realm in which I'm working. All right. Lord, this is not meant to be a religious reference. Okay. All right. every order invariant subset of Q0n to the mk has a lower z plus order invariant maximal m root. Lower z. This is the strongest notion of maximality of invariance I consider. And the multi-root form is the strongest widget gadget that I consider. So I'm actually proving the strongest thing. There is a very important part of this book, which we're not going to cover in the lecture series, or at least I don't plan to, which is that lower z plus order invariant is the strongest reasonable notion of invariance for which these results hold. In other words, if you use a stronger notion of invariance beyond lower z plus order invariance, you will get 1 equals 0. In other words, it's the natural strongest condition I can put in the context of this work. This is not a simple matter, but it's something that I wasn't planning to talk on, but I have drafts of it for the book. All right. This is the 6th lead statement of the very mathematical. This is actually not a lie. This is actually not a lie, which means it's true. This is the 6th lead statement of the very maximality, upgraded with a stronger maximality than is in the official lead statements. Okay. All right. Now that I've stated it, I'm actually going to go over all the definitions, and then I'm going to prove it. All right. So if I have a subset of dimension m times k, an m root just means that s to the m is contained in E. And roots are 2 roots. And 2 roots occur when m equals 2. In all through invariant maximality, period. In invariant maximality, I'm always dealing with subsets of Q0n to the k. All the statements involve conclusions. The conclusion of every statement is there's an S contained in Q0n to the k with a maximality property and an invariance condition, like here. You see, the root is k-dimensional. The root is k-dimensional. So you always have that. Even if I have this dimension m times k. Order invariance is something this is the most basic thing that we've talked about that drives anything even connected with this book. Order invariance. Order equivalent objects of the right dimension are one's in the set if and only if the other is in the set. And then this. Now this is the strongest invariance condition we consider, as I said in the book on invariant maximality. So we need to talk a little bit about this. So X and Y are in Q to the R, are lower Z plus order equivalent. Yeah, I was scared to use K because I was reusing it before, but I'm not using it in this context. And the conclusion is always dimension K. So I am now hereby going to do this. Okay. All right. So X and Y in Q to the K are lower Z plus order equivalent, if and only if they're order equivalent. That I, of course, want. And wherever they differ, whenever X and Y differ, we have every x, y, every other coordinate that's at least as big on both sides have to be a positive integer. So let's pretend that we're actually looking at strictly increasing sequences, for example. Both sequences would have to start off identically and then start getting into the positive integer way of life. And so it might be like 1/2. They both start off with 0, a half, a third, a half, 2/3, and then they do 1, 5, 10, 15, and the other does 2, 6, 7, 8. Right? That's if they were strictly increasing. Now, there's no requirement. This is for arbitrary sequences. So whenever they differ, everything at least as big has got to be a positive integer. And you can easily picture this. First, I recommend you picture it when the things are strictly increasing. Then it's easy to picture. And this is the fundamental equivalence relation, the strongest one. I mean, notice that my equivalence relations all involve trivialities. The regular order on rationals, and the other thing I need to know is, well, who are the positive integers, right? That's all. So I'm really looking at the structure Q, comma, Z, comma, less than, right? All right, so we now want to prove order invariant slash max slash multi-root slash Lord. So we fix an order invariant. Now the proof is going to be have a lot of commonality with the introductory proofs in the previous lecture, of course. It's going to be like the one I did with Erdős-Rado, except instead of Erdős-Rado, that's theorem 6. It's going to be more like theorem 6 prime. It's going to use the subtle cardinals, you see, instead of the Rado. All right. Now, first of all, let's get rid of the case m equals 1. This is trivial because E is the maximum 1 root of E and is lower Z plus order invariant. So we assume M is at least 2. And let kappa be a suitable large cardinal. We'll only worry about what large cardinals needed, at the end, I mean, that's a technicality. All right. So as we did in the last lecture, I defined these spaces T alpha, which are alpha cross Q01 union singleton alpha 0. Now, why do I multiply by Q01? I want to make sure that T alpha is a dense linear ordering. I want to make sure that T alpha is a dense linear ordering with a left endpoint and a right endpoint. So notice that that the left endpoint of T alpha is the pair 0, comma 0, and the right endpoint is the pair alpha, comma 0. Okay, so even more important is the full one, the big one, T of kappa. And less than star is the lexicographic linear ordering on T of kappa. First, we compare by the ordinal, and then we compare by the rational. Okay. Now, we definitely need an associated well ordering because I want to do a transfinite recursion. And so this is done neatly as follows. We use any effective enumeration of the rationals in 0, 1, starting with 0. It's important that it start with 0. without repetition, yeah. And less than star is a density ordering, as I said. Now, but less than double star, we have to worry about, we have to talk about. Less than double star is the well ordering on T kappa given by alpha pi is less than double star beta pj, if and only if alpha is less than beta or alpha equals beta and I is less than j. Okay. So that makes it well ordered. And I also want to extend it to k-tuples. It's important to extend this to k-tuples. And this is done lexigraphically, except that it's the bounded lexigraphically. That is, U1 through UK is less than double star UV1 through VK, just in case either the max of the first is smaller than the max of the second, or the maxes are the same, and we're doing lexigraphically under less than double star. Okay, so we have a well-ordered extension for k-tuples. Now we perform the greedy root, the greedy M root. There's a thing called the greedy M root. You can talk about the greedy M root without going to transfinite. You know, in fact, I probably should have told you about the greedy M root, but you know what the greedy M root is. So it's this. Z is an S if and only if you can put it in to the previous construction, if and only if the set of W in S such that W is earlier than Z, union singleton Z is an M root of E. In other words, we're building bigger and bigger roots, bigger and bigger M roots of E. And we're putting something in an M root just in case we can. And everything is done along the well ordering, less than double star on k-tuples. Yeah, I should have probably said this is k-tuples. Like the following definition of S contained in P kappa. Now you begin to understand some of the tricks I use to avoid learning tech. Okay, so, all right. Well, I guess this was already pretty clear. Yeah, I guess I didn't need to do that. I just wanted to show off. Okay. All right, so how are my jokes doing, Andreas? All right, let's see. So, all right, so it's clear that S is uniquely defined since less than double star is a well ordering on T kappa to the K. Also, S is contained in oh. Well, I'm not going to get to the place where I can raise the font to the proper size here without leaving the meeting. So I better not press leave meeting. All right, is a maximal M root of E. We call S the greedy M root. Okay. And now we want to work with this structure T of kappa. Let's keep all the data intact. Not a problem. Keep the data intact. So we have a nice structure. So now, by the model theory that we did, the classical model theory that we did, where you build you build a transfinite chain of elementary substructures that are filled out, no gaps, with no gaps. We build lambda alpha less than or equal to kappa, closed strictly increasing sequence of limit ordinals less than or equal to kappa of type kappa plus 1. So we have the last one, such that the following holds. For all alpha less than kappa, lambda alpha cross Q01, union the top point kappa 0 is an elementary substructure of the whole thing, T kappa, which has, by the way, kappa 0 in it as the top point. So this is this elementary substructure chain. And then there's some facts about this. Q alpha cross Q01 union, this satisfies the greedy construction condition. Right? In other words, we did the greedy construction condition on the whole thing. And so we get the greedy construction condition on the partial things because it's an elementary substructure. And that's first order. That's first order, being the greedy emerald is first order. So it's satisfied to be the greedy emerald of E. It's got this with this top point. And now we want to, what's really going on here is some embeddings are going on here. So we have an embedding J alpha from this crazy thing that we did. In other words, we took the old top point and replaced it with a big top point. That's what we did, right? So that goes into T alpha is the bijection, which is that goes into T alpha, which has the lower one, which is the same as this one, but it has the lower one. When I wrote T of alpha, it probably should be T of lambda alpha. Yeah, that's not right. Be the bijection, which is the identity on on lambda alpha cross Q01 and sends kappa 0 to alpha 0. This is analogous to the Gödel transitive collapse. This is Gödel's transitive collapse in a very special situation. You know, to do his magic work on the continuum hypothesis in L. See, because this monster here, that's not transitive, you see. It's not transitive like. I mean, it's slightly different than pure septic. It's not transitive like, it's got this big monster here. But now we make it transitive by replacing it down here. We get something that's elementarily equivalent, which therefore means that it must be the greedy construction. So J is an isomorphism from this thing onto some J alpha, right? Is an isomorphism from this thing onto something, right? That's clear. But that something must agree with S on here because it's the identity, because this is the identity on here. Lambda alpha. Right? But it must be the real thing. It must be the real thing, since anything in up here has S prime agreeing with the greedy emerald. It has to be the greedy emerald, right? Because of elementary equivalence. All right. Now we want to put it in the form that it's really useful for us, So we defined the trivial embedding H of alpha beta, which goes from T alpha to T beta. See, the stuff we did up here is the relationship between these partial things and the full big one. Now we want to look at two partial ones. So H of alpha beta goes from T alpha into T beta is the identity in the interior, and it maps alpha 0 to beta 0. Then this is the point. We only care, number 6 is all we care about. For all alpha beta less than beta less than kappa, H alpha beta is an isomorphism from T of lambda alpha into T of lambda beta. And we have this because we can go up by J alpha inverse. That takes us up by J alpha inverse and comes back down by J beta. Okay. Comes back down by J beta. All right, at this point, we can easily dispense with the case K equals 2. From 6, it's clear that S is lower lambda alpha less than kappa invariant with the obvious, remember in dimension 2 invariance is always trivial, almost trivial, with the obvious extension from Q0 from the non-negative rationals in Z plus to the transfinite. Then take accountable elementary substructure. And this is just a fancy way of repeating the lecture number, the previous lecture. Because remember, the previous lecture, we just did dimension 2. Actually, we also did n equals 2. Let's not worry about that right now. All right, so we can assume K is at least 3. All right, now let's let W be the set of these things. Remember, these lambda alphas were built by classical model theory with a transfinite sequence of elementary substructures, the tower. Okay, so let W be the set of lambda alpha. And let alpha 1 through alpha k be strictly increasing in W. We can use these ordinals to form a k-tuple in finitely many ways, made from alpha 1, 0 through alpha k 0. These are going to be my indiscernibles, right? These points. And pairs beta p, where beta is less than the first one, right? I can look at these. These are the ones I care about, right? And these are the parameters, right? Parameters below the first indiscernible. And I call these the shapes. These ways are the shapes. There are only finitely many shapes. And we ask for membership. What we want to know is, when is this in my S that I built? You know, that's my greedy transfinite, my greedy emerald, my transfinite greedy emerald. Well, S has more in it. Yeah. In S intersect. Yeah. Since I don't care about the top one anymore. I don't care about the top one anymore. Yeah. Okay, we want to get the same answer depending only on the choice of the beta P and the shape, right? That's the idea. Note by 6, the membership S depends on only alpha 1 through alpha k minus 1 and not on alpha k. Right? Because if I change the alpha k's, I don't change the truth in the thing because of number 6. You know, the thing about the embedding. This is exactly the situation we want to have kappa be a kappa minus 2 subtle cardinal. kappa minus 2 because this is kappa minus 1. We get n indiscernibles for exponent k minus 1. Under a countable elementary substructure and order isomorphism, the indiscernibles become 1 through n. In other words, we're doing this all in the transfinite universe. We pull it back down to the rationals with the numbers 1 through n. That's just by elementary substructure. If n happens to be less than k minus 1, then we use exponent n minus 1. You see, you can't, if n is less than k minus 1, we can't make k different indiscernibles out of it. Instead, we're using exponent n minus 1 and n indiscernibles. So in general, it suffices to assume kappa is min of kn minus 1 subtle. It's going to be the min of k and n. And let's repeat our statement and take stock at where we are. Every order invariant subset of Q0 n m to the k, mk has a lower z plus order invariant m root. Now, for fixed n and k, we prove this using ZFC plus there is a kappa, such that kappa is min of kn minus 1 subtle. And for fixed k, we can let n vary. We'll just need a k minus 1 subtle cardinal. And for fixed n, with k universally quantified, we just need, why did I write this? N minus 1 subtle. Okay. And the last thing I want to talk about is how the mere consistency of these three theories suffice over RCA naught. Suffice to this is wrong, over WKL naught. Yeah. Okay. There are two ways to show this. There are two ways to show this. One is to observe that the statement in question for free K and N is provably equivalent to a pi01 formula over WKL naught for free K and N via Gödel's completeness theorem. I think in an earlier lecture, I think that was the lecture, I think maybe it was just the last time. Yeah. No, it was lecture 3. Lecture 3. I showed you, I sketched how you use Gödel's completeness theorem to show just about everything I'm talking about forever is a pi01 sentence, as an implicit pi01 sentence. If you remember that argument with Gödel's completeness theorem. And then remark that if a theory proves a pi01 sentence, then the mere consistency of that theory proves the pi01 sentence. Yeah, I mean, I will state this more formally. I'll actually do some touch-up work on this document before I put it up on the lecture notes. It needs a little touch-up. There's a few things here, minor things. All right. The other way of showing that WKL naught plus the consistency of these theories is enough is first to assume the mere consistency and then go up to a countable model with satisfaction relation using WKL naught. Then repeat the argument, reducing to the actual rationals. So just sort of repeat the argument. When I was playing around with large cardinals, I play around with points in a countable model with large cardinals. See, the conclusions are all finite. There's no problem with infinity. You don't run into any issues. Now, I should give you a crash course in what these large cardinals are. Okay, so lambda is K subtle if and only if for all closed on. These are the official definitions. If lambda is K subtle if and only if for all closed unbounded C contained in lambda, and regressive F from the K element subsets of lambda into subsets of lambda, there exists an F homogeneous A in SK plus 1 in the K plus 1 subsets of C. Regressive means all the values are smaller than the min of the argument. All the elements of the values are smaller than the min of the argument. I think I usually state this. People state this assuming that lambda is a cardinal. I think the way I stated these things, you just assume that lambda is a limit ordinal. You don't want to get involved in what this stuff means when lambda is a successor ordinal. It's not interesting. Like, what does closed unbounded mean when lambda is a successor ordinal? All right, you don't. Okay, so and then there's the other thing, which is the advertised thing, SRP. Lambda has KSRP if and only if every partition of the unordered K tuples from lambda into two pieces has a stationary homogeneous set. And the basic results in this stuff are KSRP implies K minus 1 S a subtle, which implies K minus 1 SRP. So these interweave or interleave, where the implications are strict. A lot of information, more information than you may want to know, is already in this paper, Subtle Cardinals and Linear Orderings, in Annals of Applied Logic. I think it's in 2001. But it's easy to find that. I mean, there's even my old original manuscript in MS Word on the internet instantly, if I remember. Or it's published also. All right, so these definitions of subtle and SRP, if I remember right, are actually due to a number of other people, especially Baumgartner was very important in this. And then I actually show in here that although this is not important for the has not proved to be important in this book, that you can do this stuff on linear orderings that are not necessarily well orderings, and that these notions make sense and all kinds of wonderful things happen. That if you restate them in linear orderings, you actually can derive the statements in well orderings, the usual statements. Those are somewhat tricky to do, and that paper has that stuff in it. Might become useful someday for this kind of stuff I do now. So I think that we're done. I'm going to do a little cleanup on this thing, but I think it's likely the next lecture should be, if all goes well, the next lecture will be not on invariant maximality, but on invariant free choice. and invariant strategies of games. And there'll be proofs and derivations of the invariant maximality come from the game stuff. The plan is the game stuff, the game theorems imply the free choice theorems, and the free choice theorems imply the invariant maximality. That's the plan. So that no new reversal will be needed. And we'll reap the benefits of this later. Besides, the game theory is finite game theory. There are only finitely many moves. There's also an infinite version where there are infinitely many moves, but the finitely many moves is still independent. And then there are later versions that show that the later versions I'm working up, which show that you can turn these into board games and basically have little or no mathematical notions. And they're finite board games. Having invariant winning strategies or having invariantly strong strategies, whatever that means, would be independent, would be equivalent to the consistency of the large cardinals. Yeah, so there's some plans in the works which may affect the schedule of the lectures, but I promise to do my best to always tell the truth. Okay, and I have to make sure of that before you hear anything. All right, so I think that you've had your fill of this, and I think I'll stop here.
Yeah, thank you very much. I will now stop the recording.